into interstellar space. Launched almost 50 years ago, the spacecraft continues moving through regions no mission was originally expected to explore for this long. What makes its journey even more extraordinary is that it still communicates with Earth using technology built in the 1970s. Its onboard systems are far less powerful than modern digital devices, yet they continue sending signals across billions of kilometers of empty space. Recently, Voyager 1 has gained renewed scientific attention, not only because of the immense distance it has covered, but because of the unusual information it continues to send back. Data from the edge of interstellar space has revealed subtle irregularities in magnetic fields, plasma waves, and charged particle behavior that do not completely fit current scientific predictions. These discoveries are encouraging researchers to rethink what exists beyond the solar system and whether interstellar space is far more active and structured than once believed. The story of the Voyager mission began in the late 1960s when NASA engineer Gary Flandreau discovered a rare planetary alignment. Jupiter, Saturn, Uranus, and Neptune would align in a way that allowed a spacecraft to use gravity assists from each planet to travel deeper into the outer solar system while conserving fuel. This opportunity appears only once every 176 years, making it one of the most valuable launch windows in space exploration history. To take advantage of this alignment, NASA launched Voyager 1 and Voyager 2 in 1977, only days apart. Their original mission focused on exploring the outer planets through close flybys and transmitting detailed scientific observations back to Earth. However, what started as a planetary mission eventually evolved into humanity's first direct exploration of interstellar space. As the spacecraft moved across the solar system, they delivered discoveries that completely changed planetary science. At Jupiter, Voyager detected active volcanoes on Io, revealing it as the most geologically active body in the solar system. At Saturn, the probes captured detailed images of the planet's rings and discovered previously unknown moons. These findings transformed the gas giants from distant mysterious worlds into highly dynamic planetary systems. Voyager 2 later continued farther outward, becoming the only spacecraft ever to visit Uranus in 1986 and Neptune in 1989. At Uranus, scientists discovered unexpectedly complex magnetic activity, while Neptune revealed violent storms and powerful supersonic winds despite receiving very little energy from the Sun. By the end of these encounters, both spacecraft had already rewritten major parts of planetary science. Even though the mission was originally expected to last only a few years, both probes continued operating decade after decade. Their endurance became legendary. Each spacecraft is about the size of a small vehicle and carries only a limited collection of scientific instruments, yet those instruments continue providing valuable information from farther away than any human-made object has ever traveled. Voyager 1 still operates with an incredibly small memory capacity by modern standards, yet it continues collecting and transmitting scientific data across interstellar space. Communication itself is an engineering miracle. The spacecraft transmits with only about 23 watts of power, comparable to a household light bulb, but its signals still manage to cross billions of kilometers before reaching giant antennas on Earth. Because radio signals travel at the speed of light, messages now require more than 18 hours to arrive, and that delay continues increasing as the spacecraft moves farther away. One of the mission's most historic moments came in 2012 when Voyager 1 crossed the heliopause, the outer boundary where the solar wind can no longer dominate the interstellar medium. This officially made it the first human-made object to enter interstellar space. Scientists originally expected the crossing to produce dramatic and sudden changes. They predicted a sharp shift in magnetic fields and a clear separation between solar and interstellar environments. Some changes did occur, including a rise in galactic cosmic rays originating from distant stellar explosions. However, many other expected transitions were surprisingly subtle. Instead of finding a clean boundary, Voyager revealed a smoother and more blended transition zone. The magnetic field remained more continuous than predicted, suggesting the edge of the solar system is not a rigid barrier but a dynamic region shaped by both solar forces and the surrounding galaxy. When Voyager 2 crossed the heliopause in 2018, it confirmed many of these observations. Together, the two spacecraft showed that the heliosphere may behave more like a flexible bubble interacting with interstellar space rather than a sharply defined shell. Beyond this region lies the interstellar medium, a thin mixture of ionized gas, dust, magnetic fields, and cosmic radiation produced by ancient stars and supernova explosions. Scientists once assumed this environment was relatively uniform, but Voyager's measurements suggest otherwise. Subtle variations and hidden structures may influence how energy and particles move through deep space. One of the most fascinating discoveries involves the behavior of magnetic fields beyond the solar system. Rather than shifting unpredictably, the fields appear more organized and aligned than many models anticipated. This has raised important questions about how far the Sun's influence truly extends and whether interstellar space contains larger magnetic structures still not fully understood. As Voyager continues its journey outward, it is slowly traveling toward the distant and largely theoretical Oort cloud, a massive region believed to contain trillions of icy remnants left over from the formation of the solar system. Although the spacecraft will need tens of thousands of years to reach that region, its current path is already helping scientists better understand how our solar system interacts with the galaxy around it. Every signal received from Voyager represents more than scientific data. It is a connection to a machine leaving the solar system forever, carrying evidence of humanity into the unknown. Those signals grow weaker with time, yet they still arrive steadily across the emptiness of space like a faint echo from the edge of the cosmic ocean. The Voyager mission has permanently changed humanity's understanding of exploration. It proved that the boundary of the solar system is not a simple wall, that deep space is not completely empty, and that even relatively simple machines can survive far longer than expected in one of the harshest environments imaginable. As scientists continue analyzing Voyager's discoveries, new mysteries continue to emerge. Is interstellar space truly uniform, or does it contain hidden structures and unseen forces? How far does the Sun's influence really extend into the galaxy? And what unknown environments still wait ahead of Voyager as it travels deeper into interstellar darkness? For now, Voyager 1 continues its silent voyage carrying the famous Golden Record, a collection of Earth's music, languages, and natural sounds intended as a message from humanity to the cosmos. Whether anyone ever finds it may not matter. Its true purpose was never about being recovered. It was about exploration itself. And as long as its faint transmissions continue reaching Earth, Voyager will remain one of humanity's greatest achievements, a reminder that even the smallest creations built by human hands can travel farther than anyone once imagined and continue expanding the boundaries of the known universe. Long after crossing the boundary of the solar system, Voyager 1 continues moving through a region humanity has never explored before. Every hour it travels farther into interstellar space, entering an environment so distant and unfamiliar that even the most advanced scientific models struggle to fully explain what it is encountering. Yet despite its age and limited technology, the spacecraft continues sending back fragments of information that are reshaping our understanding of the galaxy beyond the Sun's influence. What scientists expected beyond the heliopause was relatively simple: a cold, sparse, and mostly uniform region filled with thin gas and drifting cosmic radiation. Instead, Voyager's instruments detected something far more complicated. Plasma waves moving through interstellar space appeared stronger and more structured than anticipated. Particle densities fluctuated unexpectedly. Magnetic fields showed patterns that hinted at hidden interactions occurring far beyond the solar system's edge. One of the biggest surprises involved the density of interstellar plasma surrounding the spacecraft. Before Voyager crossed into interstellar space, researchers believed the environment would remain extremely diffuse and relatively stable. However, measurements revealed areas where particle density suddenly increased, almost as if Voyager were moving through invisible cosmic currents. These fluctuations suggested that interstellar space may contain shockwaves, magnetic boundaries, or compressed regions created by ancient stellar explosions and the movement of nearby stars. Scientists also discovered unusual bursts of plasma oscillations traveling through space. These waves were likely triggered by powerful solar eruptions launched years earlier from the Sun itself. Even across billions of kilometers, those eruptions continued traveling outward until eventually reaching Voyager far beyond the heliopause. This demonstrated that the Sun's influence extends much farther into the galaxy than previously believed, interacting with interstellar material across enormous distances. Another mystery emerged from the behavior of cosmic rays. Voyager recorded changes in the intensity of high-energy particles entering the solar system from deep space. Some of these variations appeared linked to the Sun's activity cycle, while others seemed connected to unknown processes occurring in interstellar space itself. Researchers now suspect that magnetic turbulence beyond the heliosphere may shape how cosmic radiation spreads.